I welcome you all, and I hope everybody is fine. And today's target is basically to learn about operators. And all of you know that we have generated a room filled with infinite number of possibilities. And this room is called as Hilbert space. And we tried to say that what this Hilbert space is filled with. It's filled with numbers. It's filled with functions. It's filled with vectors. Now today we want to introduce other characters in the Hilbert space. I may call these additional characters as the workers, the laborers. Previously, nothing was happening. Everything was there. Let me remind you, this Hilbert space is an imaginal space. It's not an ordinary space in which you have the gravity. It's not that ordinary space which encompasses matter. No, it's an imaginal space. And in this imaginal world, we have the workers. We have the laborers. It is these laborers which give the meaning to all the states that are living in this Hilbert space. It's a different world. It's not the world that we are living in. And in this world, the order is very important. The order, you understand the order? First will come A, then will come B, then will come C. And then first will come B, then will come A, then will come C. First will come C, then will come B, then will come A. Now what am I trying to tell? What am I trying to tell you about these workers, about these laborers, whom I call as operators? If conventionally you ask somebody, what's an operator? He'll tell you an operator is something, when it acts on a vector, it changes this vector into another vector. This is the definition, the mathematical definition of operator. So we want to realize it, we want to understand. Now let me choose two characters in the same Hilbert space. The two laborers, the two workers. The name of one is A and the name of another is B. Okay? And now, these two fellows, they choose a wave function. They choose a state vector in this Hilbert space. A tells to B, okay, come on, we have this state vector. Let me act on it. Okay? And when I will act on it, obviously something will happen to it. It will reveal something. Then you will act on it. Then you will act on it. B will act on it. So when B will act on it, you will have a result. So they decide, okay, let's do it. So now what happens? You have a state vector. Mr. Operator A comes, he acts on, and the state changes. Now Mr. B comes and acts, and you have the final state. Now they both look at it, they say, come on, this is the final state. An idea comes. Now come on, let's reverse. A tells B, now you first act on the same state. Let us choose the same state. Now you first act on it, and then I will act on the result. Now what is happening? Now B is acting on the state, it changes, and A comes, and A acts on the state, changes, and when they see the result is not same. The result is not same. So what's going on? So it means in this quantum regime, when A acted, it changed the state. So it was not the state that was acted upon before. Now B is acting on a different state. So action of A on the state and then B on the same state leads to some result. And when we reverse the order, it leads to another result. This is how this world lives. This is how operators realize themselves in the Hilbert space. Are you getting my point? So when you have operators, you have commutators. There is a commutation relation between A and B. And mostly what we see that the operators do not commute. There are some operators which commute. There are some ideal operators. But most of the operators do not commute. And why they do not commute? Now they talk to each other. Because the state, the shift in the state, when A acts first, gives a different result than that of the shift of the state when B acts first on the same state. So what do we understand from this story? We understand that in this world we have operators, but when these operators act, the order of their action matters. And this is what makes your Hilbert space different from the normal mathematical formulation. The order becomes the principal action. So order matters. So changing order changes the state of the system. A, B gives you, can give you one kind of state, and B, A can give you another kind of state. But if the result is zero, you might have seen that. If you find the commutation relation between the two operators, if the result is zero, what do you say? You say they commute. So there is presence of those operators also in your Hilbert space which commute. But in most of the cases, you will find that they don't commute. Because the origin of that non-commutation is what? Come on. What is the origin of that non-commutation? Anybody? The very fundamental principle of the quantum mechanics. It's Heisenberg's uncertainty principle. Right? So the first thing is talked about, right? Now you have these states living in your Hilbert space. You have a king, boss, the boss of the Hilbert space. Who's the boss of the Hilbert space? Is the Hamiltonian operator. Is the Hamiltonian operator that evolves this Hilbert space. It's the Hamiltonian operator that gives birth to the time. It gives birth to the evolution of time. If I think about this universe quantum mechanically, the changes that are happening in the universe, how these changes are happening. These are happening through operators. And Hamiltonian operator is the main operator who is making this universe to run. So here we have an operator known as Hamiltonian operator. And Hamiltonian operator tells us, it gives us an idea about the atomic transitions. It gives us an idea about the resonance between the two states. It gives us an idea about the infinite possibilities that might exist in your Hilbert space. So that's what is Hamiltonian. Now, when this Hamiltonian is acted on the state, it certainly drives the system. I may say the dynamics of the Hilbert space, the dynamics that we can mathematically calculate, is a result of this evolution operator known as Hamiltonian operator. And finally, there is revealer. And this is very confusing. And there are many theories roaming around revealer. When you act your operator on a state, it leads us to a result. That result is given by a revealer operator. And what result that we obtain from this revealer? In your Hilbert space, in which you have large number of possibilities, there are some possibilities that align with this operator. There are certain possibilities that align with this operator. And the rest of infinite possibilities, they disappear. So what is the job of this revealer? Yes, the revealer leads to what you call as eigenvalues. And it doesn't mean that when you act on your system using a revealer operator, there were infinite possibilities, right? But when revealer comes in action, only those possibilities come in the form of eigenvalues, which align with what? Revealer. The rest of all disappear. Now the question arises, is it because the revealer tried to reveal what's the truth about the system? Is it the revealer that has destroyed all other realities of the system? Or the system has this tendency that it knows what to reveal and what not to reveal? This is an open question, but let me tell you frankly, you might have heard about quantum computer, right? Have you heard about it? Come on, yeah. We have a quantum computer being built in IBM. It is in its preliminary stage, but people work on it and they make it work. It runs. It actually runs. You can play a game with the quantum computer. and you'll never win it. And quantum computer is based on this principle that when you are not trying to reveal the system, when you are not trying to look at the system, there are infinite possibilities. There are infinite possibilities. But once you try to look at it, all other possibilities are gone. I wanted to demonstrate this thing, but I think Professor has entered. So if anybody has any question, you can ask me. So I think the idea of operator is there. We have an idea that what an operator means, and we will now go in algebraic way to define some of the important operators. Then we will do some preliminary algebra that's linked with operators. So with this, I would like to thank you all. Okay, I welcome you all in today's session. And yesterday we tried to actually understand the actual mechanism of operators, that what operators are, and we tried to imaginalize these operators as laborers or workers in the Hilbert space. And again, I would like to bring your enthusiasm, your interest, your love, your emotions for physics, because as all of you know that there's a good rate of decline in the number of students throughout the country in physics. So my motivation is basically that I want you to feel attracted towards this subject, because believe me, this is a subject that will give you some kind of peace at the end of the day, because once you translate something in a mathematical equation, you are actually understanding the language of the universe. You are understanding that how universe is thinking, how universe is acting, how universe is manipulating. And universe is not a small thing. We understand that our imagination fails to realize the actual dimensions of the universe. So you can enjoy it. The moment you have those crazy, complicated equations sometimes you encounter, you might feel very worried about them, but the moment you get them, you learn the language of the universe. So what we have been doing here is we are talking about the operators. And as I said, an operator simply, what it does, it changes one vector into another vector. If you have an operator like, say x cap, so if you put a cap on a symbol, that refers to an operator here. Now, from different books, you can have different kinds of symbols they'll be using. Like, you can have an operator that can be z cap, or you can choose an operator a cap. Or you can have some linked operators like momentum operator, position operator, energy operator, Hamiltonian operator. So what operator does? If you have a state, say I have a state zeta, I act, this zeta is acted upon by an operator a cap, it will change this vector, say into some another vector psi, right? This is what operator means mathematically. This is how we reflect an operator. Now, to start with, suppose I have an operator, and this operator is okay. I'll choose the same a cap, I use this operator on some state zeta, and I obtain the same zeta, right? I have an operator a cap, I execute it on the state zeta, I get the same zeta. What does that mean? That means this operator is an identity operator. Are you getting my point? Okay? So the operation that you have acted on this state has not changed it. The state of this vector, you're getting the same vector back, then your operator is an identity operator. And in operators, what we have, there should exist an operator which is known as inverse operator. All operators, it's not essential that every operator will have inverse. No, that's not the case. But most of the operators that we use, they have existence of inverse. So how can I write that? How can I demonstrate that? I can do something like this. So I'll be using the same thing. Okay, I have an operator A. I'm using it on the state zeta, and I'm getting a state, say phi. Okay? Now, if I multiply this equation from left on both sides by an inverse operator, how do I write that? A cap inverse. This is an inverse operator. Okay? So if I multiply this equation with A inverse operator, so I'll have A operator, I'll have zeta, and this is going to give me A inverse and phi. Right? Now, if you have an operator, you have an inverse operator, and then the same operator, the two will give you identity operator. Okay? So this is going to give you I. So what you are left with in this case, right? You are left with this zeta is what? Can I move on? Okay. So what does it mean? It means this state zeta is what? It is A inverse of phi. What does that mean? That means if you take the inverse of phi, you will be back to zeta. Are you getting my point? So I can write it on the other side, like taking inverse on the state phi will get me back to zeta. Right? So there should exist what? An inverse operator. Now let's go back to our, because we want to, there can be a rotation operator, not in Hilbert space, but we use rotation operators in certain cases. But now I want to extend this on commutators, right? Now, before we talk about the commutators, let us take an example of ijk. Okay, you have the Cartesian coordinate system, right? You have I, you have j, and you have k, right? Now let's try to go with it, and let's talk about it. So what we have, my target is basically commutator. I want to go with commutators. So what am I trying to tell you is, if I take a coordinate system like this, and if I choose this as I, this as j, and this as k, okay, here you have the caps, okay, this is a different convention, talking about unit vectors, right? But don't compare this cap with the operators, okay? So the cap on the operator tells you a different story, okay? So this is your conventional unit vector that we're talking about. So what I have I, j, and k. And all of you know that the angle between I and j is 90. J and k is 90, right? So you know the angles between these. between these unit vectors. Now, I have a state. See, try to understand. I have a state I. Okay, you can see I is here. I have a state I, and I will use a rotation operator. Say I will symbolize that as AR, R for rotation. With respect to this K is along Z cap. So what am I saying? I'm saying this A cap RZ is a rotation operator. What is it? It's a rotation operator. I will write down another operator, rotation operator, AR cap. So along X, along I, what I'll have X. Right? This is quite understandable. This is the direct geometry. You understand this geometry. Now, let us see what happens. I want to take a combination of A or X cap, A or Z and cap. I want this to act on my state I. But in both the cases, my rotation goes with 90 degree. My rotation goes with 90 degree. Right? Getting my point? Okay. I defined a rotation operator, AR, and I chose the two different axes of rotation. In the first case, the axis of rotation is Z. In the second case, the axis of rotation is X. Now, I am taking in order, see, you can see, I am using ARZ on I first. After that, I will have to use ARX on the result. Are you getting my point? So what will happen here? When you are using the rotation operator on I, you're moving this state by how much angle? By 90 degree. So what will be the result here? Yeah, come on. I expect you to answer this question. See, this is I. Okay? This is I. Okay? What is this? Suppose this is J. This is J. Now I'm telling you, I'm using an operator that moves this I by an angle equal to 90 degree. What will this I become? J. It will become J. Got it? So for this action, I will get J. So here I'll have A or X cap. Here again, I have to move it by 90. This will give me J. Are you getting my point? Okay. Now the same action you will make on J. And what you'll get? You'll get K. Right? So what will be the result here? The result is K. You understand this? This is quite simple. I chose two operators, rotation operators, moving by the angle equal to 90 degree, chose the different axes of rotation, acted them on a state I, and we found what? K. Now let me reverse the order. I mean, in this case, I first acted A or Z. But now I will first act by ARX. Are you getting my point? So can we move on? Okay. So now, the next operation that I would like to execute is what? ARZ. Okay, cap, then ARX. Acting on the state I. This is what I want. I have not written 90 here because you understand that what does that mean? What action I have taken in action. what assumption I have taken. So, what do you expect now? Now first, this operator is acting. X. X is acting on I. What you'll get? Come on.
I.
1. Okay, it will stay as is. There will be no change in the state. Because the action is with respect to the same state. Right? Same coordinate. Okay? So X on X will give me 1. Okay? So what you are left with here? A or Z. And now this is going to act on the same I. Now you have K. Z means on I, what it will give you? I, J. Yeah. No, it is with respect to Z.
Minus J.
No, it will be J. It will be the state J. Whether minus and plus, that doesn't matter. That will simply change the direction of the physics. That's not going to change the actual physics. Now what do you see? What do you see from this hypothetical experiment? You see that you are using the same rotation operators. By merely changing the order of the two operators, the results are not same. The results are not same. This is giving us an idea about the commutators. What? Commutators. I mean to say, you have a commutation relation between the two operators. And most of the operators do not commute. Some of the operators commute. Getting my point? Now what does commute mean here? If I take the magnitude of, what was it? What was the first one? A or X, A or Z, minus A or Z, A or X is not equal to 0. And if this is equal to 0, they commute. So now I will write a formal commutator. I would like to write a formal commutator, right? So how can I write that? Can I move on? Yeah. Now I choose two operators. Say I choose an operator A and I choose another operator B. And to define the commutation between the operator A and operator B, we use a square bracket like this. Then you have A, comma, B. And this is equal to what? AB minus BA. Right? And if AB minus BA equals 0, they commute. And if AB minus BA is not equal to 0, so they do not commute. Non-commuting operators. You can call them non-commuting operators. And this is your commutator. Right? Fine? Got it? Understand it? Okay. Now let's use some equations, because these equations might be useful for you. This is pure algebra. Now let me write down them first, okay? Say for example, I'll write down the property number 1. Commutator of AB is equal to minus times commutator of BA. The second one is the commutator of A comma BC. These are operators, okay? A, B, C. I have not put the cap on them, but you should understand them as operators. And then this is equal to A comma B. Then you have C plus B, and then A comma C. Okay, then the third one is A, B, comma, C. This is equal to A, B, comma, C plus A, C and B. Maybe I commit mistakes. I'm not sure about that. Okay, have you wrote down this? Okay, these are three. Can I move on?
Yes.
Right, you can tell me. And then there is another one that is, I'll call it 4, that is A plus B comma C plus D, and this is equal to the commutator of AC plus AD plus BC plus BD. Okay, this is another relation. Then we have Jacobi identity. Okay, can I move on? Yeah, I can move on. Now we can have Jacobi identity. What is that? That is A comma B comma C. There's a commutator and there's a whole commutator plus B comma, then you have C comma A, and then you have another commutator, then plus C comma A comma B. This is equal to 1. Okay. Okay. There are more. There are more like this. You can do them. Okay. You can prove them as well. But I think let's choose a couple because this is pure algebra. It's not. There's not anything extraordinary in it. Now let's choose the first one. For example, which one is the first? Yeah, which one is the first? Come on. The first one is. Suppose I have the commutator like A comma B is equal to minus B comma A. It's very simple. So from the left hand side, how can I write this AB? This AB is simply AB minus BA. Am I right? Now can I put minus outside? What will be inside? It will be BA minus AB. Are you getting? So BA minus AB is what? It's the commutator of B and A. So minus is outside, so it's minus the commutator of B and A. Is this clear? Yeah? Got it? Okay? Got it? Okay. Can I move on? I think I'm going fast. It's pure algebra. You are doing algebra here, taking care of order. So can I move on? The next one is, say for example, the next one is A comma BC. Okay, what is this equal to? This has to be equal to AB. Yeah, A comma B, and then you have C plus B. Then you have A comma C. Okay, now let's go with this. Huh? Let's get this. So again, I'll use the left hand side. Okay, so if I use the left hand side. So this is A comma BC. What will be this equal to? This will be ABC minus BCA. Are you getting it? Isn't it? Right? Okay, that's fine. So can I write this like this? This is ABC. Okay. Then if I write plus BAC minus BAC minus BCA. Is it right? Come on. Yeah. Is it fine? I want you to see it. Is it right? Can you tell me what I have done? A simple thing I have done here. Come on. Come on, man. Yeah, I did that, okay? So you can see, you can cancel these two, we'll get the 0. So I have introduced, because my target is to get the result. So, to get the result, I have to make certain manipulations, right? So what I can do now, I can write ABC minus BCA. Can I do it? Now you dictate me, you tell me what can I write. This is BC minus BCA. Okay, these are the first two terms. What about the next two? Okay, now I will take this one, BAC minus BA. Now I took first this ABC. See, I should use this. I should have used this. BAC. So here I have this here I should use. Come on. BAC. Okay. Then what I have, so this thing and this thing is gone. So we are left with BAC minus BCA plus, come on, that's hand. Yeah, come on, tell me, plus BAC. Your voices are very slow. You're not even able to, yeah. Minus BCA. Okay. Now here you see this is BC. So what should I do here? What the result is? You see, I want to do AB. I want. Okay. So here I can write this as, what is outside?
Sir,
Yeah.
last one BC bracket में
BC.
bracket में
And that doesn't matter. I can do that. Nothing wrong with that. It will not hurt me. It will not hurt me. Let us see. Okay. So I forgot what I was doing. Yeah. Here, what I have, AB. I can write A, B, and C minus B, A, and C plus. Okay. Now what's another combination? I want B out. So this is B. Okay. AC is fine. So this is AC minus BCA. That's absolutely fine. Right? Now see here you have C out. So what will remain inside? You will have AB minus BA. Am I right? Outside is C. Plus, here in the left hand side is B. Is it on the left hand side? Oh yeah. Then inside you will have AC minus CA. Okay, the job is done. So this is what? This is A comma B. And then you have C plus B times A comma C. That's it, right? Got it? Now let's choose the fourth one. The third you will do yourself. Can I move on now? Let's choose the third one. Fourth one. What was that? It was something like the commutation between A plus B, comma C plus D. Okay? So from here we had to get the result. And now let's do it, because I'm choosing this as my left hand side. So if I choose this as my left hand side, what I'll get? I'll get A plus B times C plus D minus C plus D times A plus B. Right? Fine? Pure algebra. Okay, so this is AC. This will give me AC. This will give me AD. AD. I have bad handwriting, I can't help it. Okay, then we have plus BC. Then plus BD. Okay, then I'll go to this. So here you'll have minus CA. Then minus CD. Then minus DA. Then minus DB. Okay? Now see the combination is easiest. Now this is AC and this is CA. I will write this, okay? And then you have AD, then you have minus DA, I will write it. Then you have BC, then you have minus CB, I will write it. Then you have BD and DB. What you will get? Come on, give me the answer now. So the answer will be what?
AC
AC.
plus
The answer will be AC. Yeah, plus
AD
AD, A comma D,
BC.
plus BC
B comma C
plus BD.
plus B comma D. This is it, okay? This is how you have to do. If there are more relations, okay, you will do them yourselves. All you have to do is to take care of the order and find the order that suits your commutator. So with this, I think this is enough. Should we stop here? If you have any queries, you can ask me right now. Okay, come on. So goodbye and good luck to all of you.